Welcome to another academy. In this video, we are going to discuss about the solution of different types of problems which comes under bilinear transformation and some elementary transformations. I have given around 9 problems in this video. So if you go through all these 9 problems, you can attend any type of problem under bilinear transformation. Already in the previous video, I have given the definition and important concepts about bilinear transformation and elementary transformations. I have given the link in the description box. If you want, you can refer that video also. So here, let's start with the problems. This is the first problem. Find the bilinear transformation which carries 0 I minus I onto 1 minus 1 0. See, so these are the points in the Z plane and their images are given here. So 3 points and their respective images are given. We want to find out the corresponding bilinear transformation. Okay, for this we are going to make use of the property that every bilinear transformation preserves cross ratio. What is a cross ratio? For defining cross ratio, we need 4 distinct points. Okay, if Z1, Z2, Z3, Z4 are 4 distinct points in the Z plane, then their cross ratio is equal to the cross ratio of their corresponding images, where W1, W2, W3, W4 are the images of these Z's in the W plane. So these cross ratios will be equal for any bilinear transformation. This concept only we are going to make use for finding the bilinear transformation. So for using this definition, we need to take 4 distinct points. Only 3 points are given, no. So the fourth point I am going to take Z and its image be equal to W. So here what I have, cross ratio of Z 0 I minus I equal to cross ratio of W 1 minus 1 0. Don't change the orders given here, because here the image of 0 is 1, image of I is minus 1, image of minus I is 0. If you change the order here, the problem will be wrong. Okay, so you should not change the order. Whatever order given here, that order only you have to follow. So what is the definition of cross ratio? Z1 minus Z3 into Z2 minus Z4 divided by Z1 minus Z4 into Z2 minus Z3. In the same way for W also. So here what should I write? Z minus I into 0 plus I divided by Z plus I into 0 minus I equal to, here it is W plus 1 into 1 minus 0 divided by W minus 0 into 1 plus 1. Okay, so let us simplify this expression. So Z minus I into by Z plus I into, here it is plus I, no, plus I by minus I equal to W plus 1 by W into, here this is 1 by 2. So let us cross multiply. So how should you bring the final answer? It should be of the form W equal to some AZ plus B by CZ plus D. In that form only you have to bring. Okay, so for that I am doing all these simplifications here. So here bring this 2 to this side. So it is already minus 1 here, no? So minus 2 into Z minus I into W equal to Z plus I into W plus 1. Just I am cross multiplying and simplifying. So minus 2WZ plus 2IW is equal to ZW plus Z plus I plus IW plus I. Okay, so minus 2WZ plus 2IW minus, bring all the W terms to the left hand side, because I want to write it in the form W equal to. Okay, so bring all the W terms to the left hand side. So minus ZW minus IW equal to Z plus I. So let us simplify here. So here it is minus 3ZW plus IW is equal to Z plus I. So W into minus 3Z plus I is equal to Z plus I, or simply W equal to Z plus I by minus 3Z plus I. So this is the bilinear transformation which transforms our 0 I minus I onto 1 minus 1 0. If you want to check whether you are getting it correctly or not, you check with any one of these pairs. Here for Z equal to 0, what is the image? 1. So you put Z equal to 0. So what happened? 0 plus I is I by 0 plus I is I by I equal to 1. So here also the same thing is given, no? 0's image is 1. In that way you can check for all these 3 points, so that you can check whether you have arrived at the correct answer or not. Okay, that's all. Next problem, find the bilinear transformation which maps 0, 1, infinity onto I minus 1 minus I. See, this is also similar to the previous problem, but the difference is here I have infinity. See, in the previous video itself, I have explained you that this bilinear transformation is a bijection from the extended complex plane onto itself. So extended complex plane means what? Infinity, that is complex numbers along with infinity. So for infinity also we have an image, also pre-image. Okay, so here 0 1 infinity are the given points which are mapped to I minus 1 minus I. In the same way I am going to proceed. So every bilinear transformation preserves cross ratio. So the cross ratio of z1 z2 z3 z4 equal to the cross ratio of w1 w2 w3 and w4. Okay, now what are the points given here? 0 1 infinity, no. So these are the three given points, but for using cross ratio I need to take 4 points, no. So for that I am taking z 0 1 infinity equal to the respective images. Image of z is w and the image of these points are I minus 1 minus I. Now I am going to write the cross ratio. See, first in the numerator what you have to write? Z minus 1. Yes, I have written. Next what you have to write? 0 minus infinity. For writing the cross ratio, whenever you get that z term, you no need to write that term. You leave that term. Okay. By simple calculation, those terms will get cancelled. So no need to write the term containing infinity. That is in the numerator. Along with this z minus 1, one more term will be coming, no, 0 minus infinity. No need to write that term. Similarly, in the denominator, z minus infinity will be there, no, don't write. Okay, those two terms will get eliminated. Okay, no need to write. Into 0 minus 1. So only the terms not containing infinity only you have to write. So that is the difference between this problem and the previous problem. Okay, on the right hand side same as usual. So what will you write in the numerator? W plus 1 into I plus I divided by W plus I into I plus 1. Okay, that's all. Let's simplify. So minus z minus 1 into cross multiply W plus I into I plus 1 equal to 2I into W plus 1. So here also we have to simplify this result so as to bring it in the form W equal to AZ plus B by CZ plus D. So let us multiply here. So it is minus of ZW plus IZ minus W minus I into I plus 1 equal to 2IW plus 2I. So again you multiply with I plus 1. So IZW plus I square Z minus IW minus I square plus ZW plus IZ minus W minus I equal to 2IW plus 2I. Okay, so let us simplify these terms. Minus IZW, I am writing all the W terms together. Minus IW plus ZW minus W minus Z plus 1 plus IZ minus I. That is, I am collecting Z terms and W terms separately equal to 2IW plus 2I. Now you take W terms separately. Minus W into IZ minus I plus Z minus 1 minus, these are the terms containing Z and constants. Okay, equal to 2IW plus 2I. Okay, again bring this 2IW to the left hand side, combine it with the W term and bring all the Z terms to the right hand side. So finally I am arriving at this result. W is equal to minus of Z into I minus 1 plus 1 plus I by Z into 1 plus I minus 1 minus I. So bring this minus side inside the numerator. So it will be W equal to Z into 1 minus I minus 1 plus I by Z into 1 plus I minus 1 minus I. Okay, right. So we have arrived at the result. If you want to check whether this is correct or not, you can check with any one of the three parts given in the question itself. Okay, right. Then let's see the next problem. Find the bilinear transformation which maps infinity I0 onto 0 I infinity. This is also similar to the previous problem. Here I have one infinity in the domain and one infinity in the range. Okay, so as usual what I told you, bilinear transformation is a bijection from extended complex plane onto itself. So infinity in the z plane has an image in the w plane and infinity in the w plane has a pre-image in the z plane. Okay, right. So here also the same thing. The bilinear transformation preserves cross ratio. So z1, z2, z3, z4. The cross ratio is equal to cross ratio of w1, w2, w3, w4. Here the points are infinity I0. So let me write them here. Since I need 4 points, I am taking z as one more point with its image w. So here how you should write? Z minus I into infinity minus 0. No need to write that infinity term. Already in the previous problem I insisted that if you get any infinity, omit the term containing infinity. Okay, in the denominator z minus 0 into infinity minus I, no need to write, equal to. Similarly for the right hand side, w minus I, only you write 0 minus infinity, no need to write, by 0 minus I. Okay, so very simple problem. So what we get, z minus I by z into this minus I bring to this side equal to w minus I. So w equal to, when you bring this I to this side, it will be I plus, this is minus Iz plus I square by z. So w equal to, here take LCM, so Iz minus 1 by z, Iz get cancelled, so w equal to what, minus 1 by z. So this is the required transformation which transforms infinity I0 onto 0 I infinity. Okay, that's all. So these three problems are regarding what, for identifying the bilinear transformation which maps the given 3 points onto the W plane. Okay, then the next set of problems I'm going to discuss with fixed points. That is, we are going to find out the fixed points of a bilinear transformation. What do you mean by fixed point? Fixed point means the point which are mapped to itself. Okay, that is, if you take a point z in the z plane, it will be mapped to the same point in the w plane also. If it is 1 in the z plane, the same 1 in the w plane also. If it is 2 plus I in the z plane, it is also 2 plus I in the w plane. So those points are called fixed points. So we are going to find out fixed points of the given transformation. Okay, so find the fixed points of w equal to 1 plus z by 1 minus z. So how to identify the fixed points? Just simply put your w equal to z in the given transformation and solve. That's all. So z equal to 1 plus z by 1 minus z. So cross multiply. Z minus z square equal to 1 plus z. So z get cancelled. So z square equal to minus 1 or z equal to plus or minus I. So this bilinear transformation has two finite fixed points. What are they? One is minus I, another one is plus I. Okay, for I am going to take alpha equal to minus I and beta equal to plus I. If you are asked to find the fixed points, it is enough to stop here. Apart from this, based on the fixed points, we can classify the given bilinear transformation as elliptic, parabolic or hyperbolic. Okay, so that one I am doing here. So I am going to identify what kind of transformation is it. Okay, so for that, here two finite fixed points. No, when a given bilinear transformation has two finite fixed points alpha and beta, you have to write it in this format: w minus alpha by w minus beta equal to k into z minus alpha by z minus beta. In that way you have to write and find the value of k. Depending on the value of k, we can say whether it is what, elliptic or hyperbolic, like that. Okay, right. So for writing this expression, I have find out what are the values of alpha and beta. Alpha and beta are nothing but our fixed points which we found in the previous step. Apart from that, this z and w we have no. This z is any other point apart from this alpha and beta. You take z as any other value. Since my alpha and betas are plus or minus I am going to take z equal to 0. Substitute this z equal to 0 in the definition of w. So w equal to what? 1 plus 0 by 1 minus 0. That is what? W equal to 1. So now I know what are alpha, beta and what are the values of z and w. Substitute everything here and find the value of k. This z you can choose any number. For simplicity I have chosen 0. Okay, you can choose any number and find its respective image. So now you substitute all these values in this expression. So w minus of minus I by w minus I equal to k into z minus of minus I by z minus I. That is w equal to what? 1 and z equal to 0. So let us substitute 1 plus I by 1 minus I equal to k into 0 plus I by 0 minus I. So after simplification I am arriving at k equal to minus I. Okay, so this is a negative, this is an imaginary number, no? Modulus of k equal to 1. So this given bilinear transformation is elliptic one. Okay, I have given in the previous video how to identify the given bilinear transformation is elliptic or parabolic or hyperbolic. Okay, so if you want, you go through the previous video, right? Okay, so this is over. Next, find the fixed points of w equal to 1 by z minus 2i. So for finding the fixed points, you have to put w equal to z in the given transformation. So z equal to 1 by z minus 2i. So let us cross multiply z square minus 2iz and bring this 1 to this side. So minus 1 equal to 0. So we have to find the roots of this equation. For that, I am going to write this minus 1 as I square. Okay, plus I square. Now look at this expression. It is looking like a square plus b square minus 2ab. It is nothing but a minus b the whole square. Okay, equal to 0. So is it equal to I 2 times. So this is the I is the only fixed point. If a given bilinear transformation has only one fixed point, that bilinear transformation is called parabolic. No need to go for any calculation. In the previous problem, you have done some calculation for finding its nature. No, that and all not necessary here, because this is having only one finite fixed point. So automatically you can write it is of parabolic type. Only when you have two fixed points, in that case only you have to identify the value of k. Okay, then one more problem. In fixed points, find the fixed points of w equal to 2z plus 3. See, put z, w equal to z, then z equal to 2z plus 3, then what we have, z equal to minus 3. This is the only finite fixed point. Apart from this, we have one more fixed point for this. Look at this transformation. This is translation, no, translation along with magnification. So here, for these types of transformation, infinity will also become a fixed point. Okay, so this is having two fixed points. One is infinity, another one is finite fixed point minus 3. Okay, so that's all. So these are the problems regarding fixed points. Then the next one is, in the next set of 3 problems, I am going to discuss 3 or 4 problems I am having here. We are going to find the image of certain regions in the z plane under the given transformation. This is the first problem. Find the image of the half plane x greater than 0 under w equal to iz plus I. So this is the transformation. For under this transformation, I want to identify what is the image of this region. Okay, so let us write this, w equal to iz plus I. Very simple problems. It may be looking like something complicated, but it's very simple. See, let's take w equal to u plus iv and z equal to x plus iy. Substitute it in the given transformation. So u plus iv equal to I into, instead of z, x plus iy plus I. Okay, now separate the real and imaginary parts here. So ix plus I square y, no, it is minus y plus I. So real part is minus y plus I into imaginary part is x plus 1. Now equate the real and imaginary parts on both sides. So here the real part is u, here it is minus y. So u equal to minus y and v equal to x plus 1. Okay, right. So what I have done, just you substitute z equal to x plus iy and w equal to u plus iv in the given transformation. Separate the real and imaginary parts. Now let us look at the question. What is given? Well, we have to find the image of the half plane x greater than 0. So let x greater than 0. Here I don't have any x terms here, so you can omit this. No need to take this. So here only I am having the x term now. So let us take this. V equal to x plus 1. If x is greater than 0, so when this equal to become greater than, instead of x you write greater than 0, 0 plus 1. So 0 plus 1 means what? 1. So v is greater than 1. That's all. So image of x greater than 0 is v greater than 1. Here I have represented it in the graph. So this is z plane. X is equal to 0 means y axis. So x strictly greater than 0 means what? This portion, this right side portion. In arrow mark I have denoted that. Similarly, v greater than 1 means what? This is u axis, this is v axis. V equal to 1 is this line, and strictly greater than 1 means you have to put it in the dotted line, and this portion, that is the portion above this dotted line, that is v greater than 1. Okay, so the image of x greater than 0 is v greater than 1. That's all. Next one, find the image of the circle mod z minus 3 equal to 5 under the mapping w equal to 1 by z. So w equal to 1 by z. When this is called inversion, no? So whenever you have inversion, you write it in the other way. Z equal to 1 by w. Okay, right. Now what is z? X plus iy, and w is u plus iv. So what is the region given here? The circle mod z minus 3 equal to 5. So mod z minus 3 equal to 5, no, in that one you substitute z equal to 1 by w. So 1 by w minus 3 equal to 5. Instead of w you write u plus iv. So 1 by u plus iv minus 3 equal to 5. Now cross multiply. So 1 minus 3 into u plus iv by u plus iv equal to 5. So this modulus we can separate for the numerator and denominator, and then we can cross multiply. So here the numerator will be, what is the real part? 1 minus 3u, and the imaginary part is minus 3iv equal to 5 into modulus u plus iv. Okay, so let us square on both sides so that we can take the modulus. So 1 minus 3u minus 3iv modulus the whole square is equal to, when you square it on this side, it will be 25 modulus u plus iv the whole square. So what is modulus of a complex number? real part square plus imaginary part square. So real part is 1 minus 3u the whole square plus imaginary part is 3 we know, so it will be 9v square equal to 25 into u square plus v square. So here it is a minus b the whole square, no, so a square plus b square minus 2ab. So 1 plus 9u square minus 6u plus 9v square equal to 25u square plus 25v square. So bring all u square, all the terms to the right hand side. So it will be 25u square minus 9u square will be 16u square plus 16v square. This minus 6u, when it comes to this side, it will be plus 6u. This plus 1 will become minus 1 equal to 0. Now this equation throughout divide by 16. So u square plus v square plus here it will be 3 by 8 u minus 1 by 16 equal to 0. This is a circle's equation. In Cartesian coordinates, no, the equation, general equation of circle is given by x square plus y square plus 2ax plus 2by plus c equal to 0. Here the center is minus a comma minus b. What is this a? Coefficient of 2x. What is this b? Coefficient of 2y. Okay, the center is minus a comma b and the radius is root of a square plus b square minus c. In the same way I am going to compare here. So for this equation to represent a circle, this u square v square coefficient must be 1. Okay, coefficient of u square and coefficient of v square must be 1. Both should be present and both should be equal to 1. And no product term should occur. That is uv, that product should not be there. Then only it represents a circle equation. Yes, it satisfies all the conditions. So this is a circle equation. And the center is, what is the center? Coefficient of 2x. Here coefficient of 2u. Coefficient of 2u means multiply and divide by 2. So it will be 3 by 16. So minus 3 by 16 comma. V term is absent here, no? So that is 0. So this is the center of the circle. Minus 3 by 16 comma 0. And radius equal to square root of this a square plus b square. So a square is 9 by 256 plus 0 plus, sorry, minus this constant. What is this constant? Minus 1 by 16. So minus of minus will become plus 1 by 16. Now you take LCM. So square root of 9 plus 16 by 256 or root of 25 by 256. So it's simply 5 by 16. So the image is a circle with center at minus 3 by 16 comma 0 and radius 5 by 16. So how will you write it in complex numbers? Modulus. So here it is image plane, no? So you should write W minus center. What is the center? Minus 3 by 16 comma 0, no? That you have to write it as minus 3 by 16 plus 0i. This number you have to write it here. Since it is 0i, I didn't write it here. So minus of minus will become plus equal to what? 5 by 16. Okay, right. Then the next problem. Find the image of x greater than 0 and 0 less than y less than 2 under the mapping w equal to iz plus 1. So what is the mapping given here? W equal to iz plus 1. Put z equal to x plus iv and w equal to u plus iv. Then we have u plus iv equal to I into x plus iy plus 1. It's equal to ix minus y plus 1. Separate the real and imaginary parts. 1 minus y plus ix. Equating the real and imaginary parts, you get u equal to 1 minus y and v equal to x. So what is given in the question? X is greater than 0. Another one is 0 less than y less than 2. So x is greater than 0 means what? V is greater than 0. Let us come to this side. It is given 0 less than y less than 2, no? But here it is 1 minus y. So throughout you multiply by minus. Whenever you have an inequation like this, when you multiply it by minus sign, this less than symbol will get reversed. If it is less than, it will become greater than. Okay, so 0 greater than minus y greater than minus 2. Now add 1 throughout. So 0 plus 1 is greater than 1 minus y greater than minus 2 plus 1. That is 1. This is 1, no? 1 greater than 1 minus y greater than minus 1. This way how we can write? Just to reverse it. Minus 1 less than 1 minus y less than 1. But what is 1 minus y? U. So minus 1 less than u less than 1. What I am doing here is, they have given the condition y lies between 0 and 2. I am rewriting this given condition in terms of u and v. That is what we are doing in this problem. So if the condition is given in terms of x and y, let us try to rewrite it in terms of u and v. That's all. Okay. So what are the region given here? Minus 1 less than u less than 1 and v greater than 0. So this is the image for the given region. Okay. The final problem. Find the image of the rectangular region x equal to 0, y equal to 0, x equal to 2, y equal to 1 under w equal to iz. So this is a rectangle. Rectangle means line. It's a region bounded by 4 lines. We are going to find its image under w equal to iz. The same way, just put z equal to x plus iy and w equal to u plus iv. So then after that you separate the real and imaginary parts. So here the real part is minus y and the imaginary part is ix, no? So x. Now u equal to minus y, na? So for y what they have given 0 comma 1. So when y equal to 0, u equal to 0. When y equal to 1, u equal to minus 1. And for x they have given 0 comma 2. So when x equal to 0, v equal to 0. And for x equal to 2, v is equal to 2. So this is again what? Rectangle. Okay, so the image is also a rectangle bounded by u equal to 0, u equal to minus 1, v equal to 0 and v equal to 2. That's all. Thank you.